So I've listed the contents of today. So of course we had a short introduction. I'll be talking about the use case description, and then we'll have a brief technology overview just to set the baseline on what we understand as semantic models. After that, we'll take a look in the live demonstrator, the proof of concept. After that, I'll give the word to Andrea, and he'll take you along on the distributed ledger analysis and how it works. As the last theoretical part is given by Cornelis of the semantic team, and after that we'll have some time for questions and discussion, of course. So I'll start with a short video, and I'll talk over it because that might be better. So a lot of trucks travel over our roads, and we don't always know what's inside them. So in the case something goes wrong, we have a big problem of determining what has happened and if it's dangerous, if a dangerous situation has emerged, and what actions do we need to take. So the main things we want to find out in this situation is what is transported by a truck. We currently don't exactly know in an incident situation what is inside the truck. And normally in the current situation, a few calls are being made to the logistic provider. What was inside your truck? What is going on? And also, if, for instance, there's livestock or chemicals, it is not clear enough what has happened. So an example we got from somebody at the 112 control room is that a truck has tipped over, and we get or the control room gets the knowledge of that it's filled with chicken. Okay, so the animal safety rescuing team gets there with a lot of nets to catch the chicken, and when they arrive, it's apparently frozen chicken. So this has actually happened, and it's hard to determine what is inside. Also, we want to know, of course, where the accident has happened, so we can dispatch emergency services efficiently. This is this is just an overview of things we want to solve. So what are we going to show you in the next slide, and also in the use case? We're going to go step by step through a story of a dream scenario. Thereby, we identify the relevant stakeholders, so which parties are involved, and also we show, not in super detail, we'll get to that later, but we'll show in a generic way where data is coming from and who is sharing which data. So I'll start with describing our dream scenario use case. So it all starts with a logistic provider we call Janssen Logistics, and they receive an order to transport something from A to B. Okay, so this logistic company makes an itinerary and creates an ECMR message, the electronic freight notes, and this transport company is specialized in transporting dangerous materials. So in this case it's going from a chemical concern to another concern who probably does something else with it, and it needs to go from here to there. You see it on the board computer of the truck. Okay, so next step is the truck driver gets informed what is inside the truck. Okay, we're talking about hydrochloric acid. So that's, it sounds pretty dangerous already, and it is quite dangerous. So it can go right, but if something happens, we have a problem on our hands. So now we start the itinerary. The truck starts driving, and they start driving off. Everything is fine. But then, while being on the road, something strange happens. The truck passes the windshield, and the truck driver gets scared. He hits the brakes, and before he knows it, a car has driven itself into the back of the truck, and we have an incident situation on our hands. So Well, the truck detects this, and because of all its sensors and its implementation of eCall. eCall is the system already available on personal vehicles and light commercial vehicles, which detects if an incident has happened and is able to send vehicle information to the 112 control room. We'll get to that later in the next slides. So it sends us a message, and this message is received in the 112 control room. We see somebody sitting here behind the screen with the headset on, and he gets a message popping up. It says an eCall prio message coming from this number. Okay, what is going on? He also sees the location of the truck, so the last 3 locations, and from that he is able to derive the direction and also the location. Also for well, it's actually quite useful to know the side of the road it's on. So if the GPS is not that exact, it's able to determine it in this way. What is in this eCall data? Well, we can think about things like the vehicle identification number, ADR information, so it's information about dangerous goods, the model or type, the weight of the truck, the fuel type of the truck, and as I mentioned before, the location. Okay, so in our dream scenario, the 112 control room is going to make use of our great solution, where he is going to use the information he got from the eCall, so the license plate and the location, to request information about the cargo. So we'll get to that later in the live demo, and I'll show it to you as we actually do it. But this is just to give you a brief well, intro to that. So based on the VIN number from the eCall message, a link is being made with the RDW, which holds a registry of converting VIN numbers to license plates, which have been registered to certain trucks and also to certain companies. And well, this is just a fast forward, but in the end, the 112 control room is able to access cargo data and also more specified ECMR data. So here we see liquid. It's a liquid bulk. It's a well, it's a flammable chemical, and it's hydrochloric acid with certain UN codes. Also, no, we'll get to that later as well. Is that the situation where this incident has happened is a very relevant cause for a 112 control room to ask this data or request this data from a party who holds it, and therefore, like it would be not or unnecessary to ask for data that was relevant 2 weeks ago. This is a bit about access policy, but I'll also show you more of this in the live demo of the solution. Okay, so now we know what is inside the truck, what type of emergency services need to be alerted, what kind of trucks does the fire department need to send, and what do we need to clean it up. Just to be of aid, the Rijkswaterstaat gets this information as well, the information they need. So the location and what type of stuff are we dealing with. And they can help by blocking of roads and sending road controllers to dispatch or divert the traffic. Okay, so a brief overview of what we just saw. Well, the car hits the truck. It sends out a message. This is the eCall message. It comes into the 112 control room. It's hydrochloric acid, 25 tons. The Rijkswaterstaat blocks off certain roads by putting red crosses above the road, and we create an environment where emergency services can do their work safely. Okay. So just an overview of what we just saw. Well, we saw a truck itinerary being made. We saw what happened in this incident situation. It can literally be caused by anything, also attack. The identification was well, rapidly done due to the implementation for eCall for heavy goods vehicles. Currently, it is not implemented yet, but it's work in progress. But it's a bit of out of our scope. But we well perceive this this will be future implemented in the future. And of course, the use of our metadata search engine. Okay, and what kind of problems did we solve, or at least enhance? We created a rapid overview of the situation. Also, the metadata search engine was able to determine that because of the incident situation, access to certain cargo data was relevant. Because of this, multiple parties know what is going on, and we are able to enhance their risk assessment process. And as I mentioned before, because a certain situation is happening, we don't want to share data always, but in certain situations we do. And yeah, this is being made safe by the MSE. I'll also show a bit more about the authorization policies later. Okay, so I'll take a short sip of water because I get a kind of dry mouth when I'm talking. But we'll go to the semantic model basics, because all the data we need or we use in this presentation, we have structured it among in the form of semantic models. And what do we understand the semantic models? Well, we have we can compare that to the data we know, or the structure we are used to, which we can call relational data. So on the left, you see here that list. If you would make an Excel sheet, you would put everything in a list and say, okay, this is a transport means ID, and it's 1, 2, 3, 4, and you put in some information here, and you put some information here, and it's basically, this is the identifier, and this is the value, and well, it's just a list, so it's quite basic. And if we look at the picture on the right, the graph data model, I don't know, maybe for me 1.5 years ago it was quite new as well. And I see here we have each, for instance, a vessel, and it can be a truck or a vessel or whatever, and it all has a relation with each other. So or it identifies as a certain something. So a vessel is identified as a transport means, we see here, and it has a unique ID, so we can call it by its ID. And it also has a nationality, so it comes from the Netherlands. So it has the nationality NL. But a vessel is, of course, meant for a certain purpose, and it has a cargo. So the cargo has a nature, and is it part of the? Do we need to pay tax over it? Is it in the form of a container? Does it have a certain weight, and does it have a certain ID? And we can think in relations of data with each other. So instead of making a certain list where the data is just the data, we can link data of what it actually is and what it means, and we can put meaning to it. And in the end, we can also start being rational with it by arguing with it, saying like, okay, this type of cargo was on this vessel, but the maximum size, the maximum size is this, so a certain cargo is not, or another cargo can't be put in there as well. We can do reasoning with it basically. Then another part of semantic models is that where we want data systems to talk with each other when they all use different semantic models. I see syntactic. I think it's an autocorrect mistake by PowerPoint, but never mind. But they all talk in a different language, and every time we want those systems to talk with each other, we see a translation step. So we see cross-translation steps here, we see a translation step between this and this, and it takes a lot of time, and also it increases the chances for error. And if we look at the right side, while using a semantic model, oh, no, I think the synthetic, okay. While using a semantic model, we all make use of the semantic model. We all talk the same language, and we can even reason with the properties and entities we have. So it's way more efficient. It allows compatibility, and yeah, and therefore also the interoperability is improved. Yeah, and yeah, we have of course some quality checks, but if we all talk the same language, we can correct each other quite easily. See if value is logical. Okay, then it's time for our live demo, which I prepared. I need to stop sharing my screen and I'll reshare it again. Let's see what is useful. Yeah, here we go. Okay, and I'll go to it. Well, with the slow pace, not to give you too much inputs at the same time. So in the screen we have two sides, and the left side we see here is the user side. So this is the graphical user interface the user sees, and on the right side the gray part, we see what is happening in the background of the process. This is just useful to show you how data is shared, or yeah, how parties talk to each other, and also to see how the authentication part works. Okay, so we have two types of users here, and we'll start with the LSP, the logistics service provider, and then we'll go to the 112 control room employee. So from the perspective of the logistics service provider, we want to select the truck, and also mentioning this demo, a lot of these steps I will show you now would normally go automatically, but just for the sake of this demo, I will go through them step by step. So it's supposed to be super fast, but for the demo, I'll go through it slowly. So we have an itinerary of the truck 12 ABC 3. So it has already two events. So the first event is a load event in Madrid, and it was loaded hydrochloric acid. And also in LTM load, sulfuric acid was loaded, and well, now something has happened because we want to discharge sulfuric acid, and that is happening. So we want to execute this action. Okay. Well, okay. This is what we do as the logistics service provider, and this is an action well you can expect. So that's basically all the action we do for the logistics service provider. And now we'll switch to the 112 perspective. So we'll have to log in as a 112 employee. So at the start of the day, we put our credentials in there. And currently it's test at 112.nl, but it can be anything, of course. So we're logging in. And the 112 system checks whether we are an actual user and our username and password are correct. Okay. Okay, we are the correct user, and in return, the 112 identity provider, so the system of 112, gives us a token to yeah, validate that we are actually a 112 user. And we can see this token. It's a string, so we can show with this token we can show, okay, we are really a 112 employee. But the next thing we want to know is can we get access to the metadata search engine? And we are using the token we just received from the 112 identity provider. Okay, this is however not enough, because the MSE wants to know, okay, didn't you use a fake token, or did you come with something yourself? So it checks again with the 112 identity provider. Did you give out this token to this person? Is this the correct token? Okay, it is. Then we can go to the next step. Okay, then we want to know, is 112 a party we want to give access to cargo data? And this is done by involving iShare. iShare is a system which holds a registry of who gets access to what. And well, it has a lot of authentication policies. But iShare says, okay, 112 is a trusted party. We know them, and it's fine. It's okay. Okay, so the metadata search engine says, okay, this is fine for you, and you seem to be an okay user. We're providing you with the supply chain visibility ledger token. So this is our second token, and with this token, we're being able to say the metadata search engine has validated this as well. And this also means we can go to the next step. Okay, now the incident situation we just saw in the previous use case. So an eCall message comes in at the 112 control room, and as I mentioned before in the story, the eCall message contains a vehicle identification number and a location. Okay, what we see here then is that the vehicle, the VIN is translated to a license plate, and from there on we know the license plate and location. And what we want to do now is based on this information we have, so the two facts, we want to obtain cargo data. And we think it is relevant to know because an eCall message is not, well, not nothing. So we need to act. So we want to know the cargo data. Okay. The token we received before, the supply chain visibility ledger token, which we received before from the supply chain visibility, from the metadata search engine, well, we use that again, and we want to get cargo data. Then the metadata search engine will say, okay, you want to get this data, but is this data relevant to you? So these are, well, these can be a lot of authorization policies depending on has the truck departed in the last 24 hours? Has the truck departed at all? Has the truck departed in 2 weeks? Well, if it's 2 weeks ago, why would you need incident data? It's not a relevant cause, you won't get access. But in this case, we have a relevant situation, so we'll go to the next step. And it checks, all right, and it says, okay, this is the cargo data, pretty basic, and it's dangerous, it's not dry bulk, it's liquid bulk, it is this type of size, it can't exceed this and that, and there's a UN code for dangerous class right here. Okay, well, we want to know a little bit more, and we want to know the ECMR data. So this is stored on an FT by an FT provider. I'll show you how this works. So again, we want to make sure in the session that we're still dealing with the 112 control room employee. So we'll re-request the 112 token, and we get that back. So we have a fresh token to do the same. It is a bit the same as the process we did before. Then we go with that token. We go to the FT platform and say, okay, we are 112, and we need to access this data. It says again, okay, did you get this token at the 112 identity provider? Yes or no? And the 112 identity provider says yes. I actually gave this token to this user, and it's all right. Then iShare says again, okay, is 112 user we can trust? Can it use this type of data? And the FT platform has made a certain decision on this, and it says, okay, fine. Okay, then again, the authorization policy, which I told about before, is this relevant for you to know? Yes, okay, it is. And then we get structured data, structured data, which has been structured by the semantic model, so we can interpret it the way we want, and we get ECMR data. So the cargo quantity, what type of lead is this, the mass, who can we contact to inform about this cargo. So that is Janssen, which I mentioned before in the use case overview, and well, this part of the process basically ends here. So the 112 control room can, well, identify what is going on and dispatch the right emergency services.
So I'm going to speak about the general architecture. The base point of the general architecture is the distributed ledger, the blockchain. It serves as the backbone of the whole infrastructure. It's where data is stored immutably and enforcement of smart contracts happens. The distributed ledger is based on Corda, and it's what we call layer 0. On top of that, there is the Coda API, which is the interface to the infrastructure and provides easy access to the network for external services. And the Coda API is what we call layer 1. On top of this stack, we have the Semantic API. This is where the validation of data model happens according to semantic rules and semantic web technologies. And it's also the point of contact with the user interface. And this is our layer 2. So as you can see, we have a clearly stratified pile, and each stage provides a specific functionalities. So how is the journey of data once they go through the user interface and get in touch with this stack? The first point of contact is indeed layer 2. There, the semantic validation happens, as well as the token validation to authorize the access. If everything goes okay, data is forwarded to layer 1. L1 is the interface to the Coda network. It is connected to a specific node, and its job is to handle and forward data. Once the data reach the Coda node, the transaction is composed, a consistency check is performed, contracts are executed to further ensure legitimacy and rules application, and data is shared with other nodes in the network according to agreed logic and permissions. So the crucial part of this stack is clearly the Coda network. So let's have a look at why we chose to go for this platform. So Coda offers a number of reasons that leads it to be one of the most adopted distributed ledger technologies at all. Namely, we can count on reasons related to technical aspects, reasons related to sustainability, and reasons related to development reliability. So proceeding with order, confidentiality is definitely the #1 strength of Coda. In the trade-off between immutability and confidentiality, Coda does a very good job preserving the most privacy without giving up its distributed nature. Confidentiality is also extremely important as it is the key for data sovereignty. The network of Coda is highly configurable, which also leads it to be easily expandable. As for sustainability, Coda, unlike Bitcoin or Ethereum, is not based on proof of work. The options available for consensus mechanism are both high speed, high trust, and also low speed, low trust as well, depending on the needs of the application. It's also worth to mention development reliability because in the field of blockchain and distributed ledgers, technologies are being born and dying at a fairly high rate, which means that finding a stable solution is a crucial issue for the long-term success of a project. Coda is widely used, so there's wide support freely available. There is a high number of developers, both adopting and contributing to the platform. The repository with the code has a very good rating on GitHub, indicating high quality, and updates are frequent. In order to better understand its capabilities, it is worth to have a high-level overview of its main characteristics and what makes it different from other blockchain technologies. So how Coda is different? Let's first have a look at a very general overview of the basic mechanism in place in other blockchains. Let's suppose to have a set of peers. They all are in the network. They perform transactions and share information with a subset of other peers. They disseminate all data and eventually agree on one truth. But how does this compare to Coda? Let's suppose we have again a set of peers who communicate with each other. First big difference is that in Coda, information is not shared with the whole network. Let's, for example, look at the pairs on top. When they together perform a transaction, they agree on a fact. They are creating a piece of reality only they are aware of. The same thing can be done by every other subset of nodes. They perform a transaction together and they agree on different facts. Contrary to other blockchains, within Coda, there is no single source of truth. Nobody can see facts that don't belong to the set of transactions they build. And reality is built as a collective puzzle of facts where everyone sees a different part of it. The natural question from here is, if there is no single source of truth to rely upon, how is consistency of data ensured? Let's have a look at the green transaction at the bottom. Every time a transaction is built, its hash is also computed. The hash of the transaction works as a fingerprint, which is cryptographically tied to the transaction itself. Now, every transaction undergoes the same process, after which a new actor comes into play. So here we can see that the fingerprint of the transaction, which contains very limited information of the transaction itself, but it's a proof that such transaction happened, is sent to an entity called notary. It registers the fingerprint of the transaction in a ledger that the notary is responsible to keep and manage. The same thing happens for fingerprints of all the transactions happening in the network. This way, the notary can have an overview on everything happening in the network and ensures consistency of transactions and data. This principle of separation of powers between notaries and peer nodes is especially effective if we think to the degree of customization in terms of privacy design. Data between peers can be shared on a need-to-know basis, guaranteeing one of the highest level of confidentiality. At the same time, the entity in charge to have a broader view on the network, aka the notary, can't have a detailed and deep view on data exchanged among peers. Such separation is well reflected also on a communication level. In Coda, we have two main communication levels, as it's easy to anticipate. The first one is between notaries, and it works through a consensus mechanism, as all other blockchains do. The second one is between peers, which on the other hand works via peer-to-peer communication. The two levels are clearly on two separate abstract planes as they do different kinds of tasks, but indeed there's a bridge between them as peers register their transaction to a notary. So the key points about our distributed ledger infrastructure are the following. Coda can ensure full sovereignty over data, which means that if, for instance, the two peers on the left together perform a transaction, they'll be able to see it, but no one else will. And this can happen in whatever configuration of a subset of nodes. Three peers can perform together a transaction and everyone will see only what's legitimate for them to see. And one can also perform a transaction with itself, which is useful when, for example, you want to timestamp data, but you want to provide a proof only at a later stage. As we can see, flexibility is very high, and this applies to network configurations too. We can have a network with only one notary and all nodes connected to it and between each other. But we can also have, for instance, a network with two notaries connected to separate subset of nodes, and nodes connecting only to subset of other nodes. These are just two examples, but there's a lot of customization one can do. The network is also easily expandable. It is possible to add a node that transacts with one peer only, or to add a notary and connect it to other notaries and nodes and so forth. Let's now have a look at the current configuration that we have adopted for this proof of concept. As you can see, peers have been converted into servers because for this trial, requirements were better fitted using one node per member state. We also have one notary alone that keep track of transactions at the level of European Union, and information is shared on a need-to-know basis, which means in our case, the transactions performed by two countries are invisible to a third one, ensuring a fairly high degree of confidentiality. Of course, as I said, this is a test network for our trial, but things can be wildly different at choice. We could have many nodes for different institutions in a country and one notary per member state, for instance. Okay, I now want to move away from the presentation in this slide, and I want to show you this. This is the Coda Node Explorer. So it's a software that allows us to have a look at what happens in what we've called layer 0. So at the layer of blockchain, of the distributed ledger. We are now connected to one specific node. This node is the one in the Netherlands, as you can see on top right. And we can have a look at other nodes connected within this network. So we can have here the list of nodes connected. We are this node, and we have a node in Spain, the notary is in France, and another node in Italy. And we have the tab for transaction. Give me a sec, because this isn't supposed to do like this. Okay. Small problem. I will log into that again, and I think that the sharing screen is giving problems. If I will keep having them, I will have backup screenshots to show you. So I'm now connecting to our remote machine. Backbone is stored, uploaded there. We're using an SSH connection, and these are my credentials, and see if it can work. Okay. Okay, here we go. So we can see also on the map, as I was mentioning, the geographical distribution of the nodes. And yes, this is the list of transactions. So we are having a look at transactions happening where the nodes in the Netherlands is involved. So transactions are creation or modification of data in the ledger. So for instance, we can open this transaction here and see that a new piece of data is created, namely an event of type load. This is a load event. In the event, digital twins are linked, and these are the reference for the digital twins. In this case, one of these is a truck and the other one is a cargo. We have a location, which refers to the country that this event relates to. This transaction is shared with participants. So it started from the node in the Netherlands, our node, and it has been shared with the node in Spain. I want to show you another type of transaction like this one, because here we can see that instead of a creation, we have a modification of data. So we had the previous data, a planned event, and now we are executing the event. This is the transaction, and the event is now executed. So this is to show you that you saw things happening in the live demo from a nice user interface, but that was not all. Things were actually happening under the hood at the level of blockchain. Last tab I want to show you is this one. So transactions are creation or modification of data. These are the actual data. So we can see that in the ledger, it is stored a cargo. Those are all the parameters for cargo. We can also filter data. These are the events currently stored. One thing important to notice is that our visibility is affected by the node we are connected to. So here we see all this stuff because we are connected to the node in the Netherlands. But I want to show you also this one. We are now connected to the node in Italy. Italy was not part of the transactions. The transaction you saw happening via the user interface were between Spain and the Netherlands. So we are on the same network, same list, but if we go, okay, this is at the end, another error related. I'm going to open a new instance of this, and I can anticipate you that the list of transactions will be empty. So this is not the same login. I'm now connecting to a different port, which means I'm connecting to a different node. Information. Nice. Okay, we are on the network and we have a nice empty list of transactions. So this relates to confidentiality. We are not just simply limiting the access to information. The node in Italy never saw transactions happening, so is not aware at all that those transactions happened. All right, this concludes my part. I think I can leave the floor to the semantic team.
I will turn to the question not of how the data is transferred, but which data is transferred. What is the data that we actually transfer? What does it look like? And for that, we developed a semantic model. which we also sometimes call an ontology. And for that ontology, for the semantic model, we used several documents from the federated project as our input. First of all, the federated master plan. Here on the center of the screen, we see the federated semantic model as it was proposed, and on the top right, we see the federated flower model developed by Roeland. Next to that, we had numerous sessions with our colleague Wout Hofman. We also used the UNEC standards, and we had a roadside accident and spot market use case that were use cases that drove our development. And in the flower model, we see on the top right there the event is the circle in the center. And we also saw in the description of the architecture that an event is the actual thing that is being transferred on the network. So also our semantic model focuses on modeling an event and modeling everything that is associated with a specific type of event. And I'll make that clear with an example. But first, I want to explain what the result was of our semantic modeling process. First of all, we developed the ontology, so it really describes the structure and describes everything that is allowed in the model. Next to that, we created several data instance examples to show how the semantic model can be used. And third, we created several data validation and data integrity rules to describe the constraints that the instances should adhere to. But first, I'll give an example of an event. And an example of an event that may be put on the ledger is an actual time of arrival event, an ATA event, which we can see here. And it is an ATA event because it has milestone start and the datetime actual. But there are several objects in the domain that are associated with this kind of event. And first of all, that is the actual location. So, for example, it may be an event that at that time something will arrive at the port of Rotterdam. And secondly, what is associated with an ATA event is the actual truck that will arrive at that location. So next to a physical infrastructure, we also have a digital twin, or a physical object that is associated with this event. In this case, it is a truck. It can have a vehicle identification number, and it also necessarily has a license plate. But next to that, the truck also will have additional classifications. It will have additional information about it. In the use case, we saw that there are some specific dangerous goods in the truck. And all the dangerous goods, we take them from an external library, from an established standard. So all those established standards we put in a separate, as we call it, a separate module we call classifications, where we can refer to standardized vocabularies, such that we can define for this truck the nature of cargo as dangerous, and also give it a hazmat code. And in this way, we have then visualized how an ATA event would look like. But in Andreas' example, we already saw there are several or many different types of events. Also a discharge event, load event, stuffing event. So to turn this example into a real model, we generalized the approach. For an event, we modeled all the various types of events. For the digital twin, we modeled the various transport means and types of equipment and products and goods. And also physical infrastructure, we generalized beyond just a port to also the infrastructure for other modalities, such as inland waterways and the railways. And if we generalize all the yellow circles, we get our eventual model. And here, as an example, I'll zoom in on the physical infrastructure. Because then you can see several of the concepts that are in such a module. And in this module, for example, we consider infrastructural objects such as a port, anchorage, airport, and a hub. And in our model, we do not really specify it further than these kinds of subtypes, because this is the point at which our model can be extended by models from, for example, the airways, which can extend the airport into various types of airports, or from the inland waterways, which can extend ports to all various kinds of ports on which the inland waterways has the expertise, and we provide this level of detail. And a similar thing, the similar extendability is the case with a digital twin. In the case of transport means, we do not specify it further than objects like a locomotive, vessel, truck, airplane. And in the case of the vessel, that can be again extended by a standard developed by the Inland Waterways Authority. I'll again zoom in on the event. Because, like I said, there are many types of events that can be shared across the architecture. And those kinds of events we see here in purple. And I have to say that this is not an exhaustive list, but when there are additional events, those can also be added to the model. And these are in purple because we call these inferred events. We do not specify the need to exactly input an actual time of arrival event, but we want the model to infer based on the, in the example, the digital twin and the physical infrastructure, to infer that it should be an actual time of arrival event. With this structure and with the example, we have specified which events can be entered on the ledger. But we also want a mechanism of checking the validity of the events. And that's the third part of the model, because maybe the data that's entered is not entered correct. We saw in the previous example that the truck had a license plate. And of course, there were constraints on what a valid license plate is and what is not. So in this example, we have two trucks. Both have a license plate. And as you can already see, one is a valid license plate for a truck and the other is not. But we formalize that constraint into what we call a shackle rule. I give here the serialization, but I highlighted already the two important parts in red and blue. In the red, we can see that every truck should have a minimal count of 1 for a license plate. So each truck should have a license plate. Well, that is valid for both trucks in this case. But we also gave a pattern that the license plate should follow. And in this case, in a regular expression, we wrote the two valid license plates for trucks. And then we can see that the first truck does not have a valid license plate, but that the second truck does have a valid license plate. And then the constraints, the data validation rules provide a report on the validity of the data. And you can say that this event is not valid because, for example, the truck does not have a valid license plate. And that is how we check the constraints of the data. Now, before I wrap up the presentation, I want to zoom out a bit and see how the event can also play a role in the whole use case, beyond just registering events on the ledger. And for that, we gave this overview of a cargo trace. Because for a cargo trace, basically also is in our structure a sequence of events. Because a cargo trace can start with the packing event, then several load and unload events, and at the end an unpack event. And this is also very relevant for the accident use case, because we need to know exactly what was inside of the truck. So we need to follow all the load events where the cargo of this accident was involved in. And in the same way, we can also find a trace of the transport means, also called the itinerary, to gain information about where the truck was headed or where the truck came from, such that we can send the appropriate information about the accident to the relevant authorities. And in this case, the itinerary would be the sequence of load and unload events, because there the same transport means consistently is involved in. So we would infer this to be the itinerary. And that is the eventual goal of how we apply the events. And with this high overview, I want to give the word back to Victor. I think Victor will take over with a summary of what we have demonstrated.
So these are some of the things that we could do. So the first thing we already are going to do for the next phase in the project. So it's developing it into the basic data sharing infrastructure by interfacing to cargo node, port base, and potential trade lanes, and supporting the Singapore customs case. In the same way, we could apply it to the Benelux pilot. So then the Belgium could have a node, Luxembourg could have a node, and the Netherlands can have a node. We can have the dashboard that Andrea showed, just monitoring what goes on and to see what happens. We have to choose for notaries, who's going to be a notary in there. So that can be done. We could further refine what we have now as a use case and discuss it with 112 and emergency services. is this what they want? Is this what they need? We could interface with EDW, which is not yet done. So there are potential extensions over there. Like what we discussed, and I think the guys from Rijkswaterstaat are gone, but we can apply it to vessels, barges, and implement it for inland waterways. And in the end, what we could do is generalize it for all types of mobility, cargo types, by integrated the model, the ledger, and somehow the GUI. So to make it fully flexible, to have the model expressing, how do you say it, all the requirements, all the data requirements, and then easily implemented, have it supported by the ledger and the GUI. So these are things that we are going to do, the first step, and potential things with question marks that we could do. So this is a bit for discussion.